Okay, welcome to the video where we build on our understanding of rational functions and add on slant asymptotes or oblique asymptotes. So when the degree of, I'm going to say the numerator, but they're going to say p of x. So we'll say p of x, and I will say the numerator is exactly 1 degree higher. That's the idea. Exactly 1 degree more. It can only be exactly 1 degree more. I guess when the degree of p of x is exactly 1 more than, because of English, you know what I mean? The degree of q of x, which is the bottom, which is the denominator. Whoops. So what happens is if the degree of the top is exactly 1 more than the degree of the bottom, let me just show you what I mean. What degree is this? Top. You can just say it. Degree 2. What degree is this? 1. Is 2 1 higher than 1? 1 plus 1. Okay, cool. What degree is this? 2. What degree is this? Okay. Is it 1 less on the bottom? Yes, it is. Cool. Let's try one more just to kind of get the idea. What degree is this top? Degree 3. What degree is the bottom? Degree 2. Is it 1 higher on the top? That's it. It's a slant asymptote if you have that. Does that make sense? So the way we're going to find it is we're going to use long division. So basically, the way that we're going to draw in this oblique asymptote, and when we say oblique or slant asymptote, right, that's this right here. So this does complicate a little bit, but you still have like 4 sections, right? Generally, they're going to be across from each other. There are a couple odd situations where they're not, but we're basically just going to take the quotient and we're going to ignore the remainder. You may want to highlight ignoring the remainder because at some point you're going to be like, what do I do with the remainder? And I'm going to say, like I said, you ignore the remainder. Okay. So you're basically going to use long division or synthetic. I would probably use long personally because it's not always going to work with synthetic. And then that's going to be the equation of the slant asymptote, just like that. So let's synthetic this one just because it's very syntheticable, okay? So -4 is our root, and we're dividing that into 1 minus 1 minus 14. So we have 1, we have -4, we have -5, we have 20, and we have 6. So because we have that, what is that going to be? Well, we're going to ignore the remainder. Boom, see you later, remainder. X minus 5. Y equals x minus 5. That's the slant asymptote. You would just draw that in as a dotted line, and it would be a guide for you when you're drawing this in, okay? So it kind of jumps into the horizontal asymptote situation. Bigger on top, none. Well, there's one situation where there's bigger on top, and it's a slant, right? A slant asymptote, when it's 1 degree higher on top. So you probably could do the second one. Let's just go to the fourth one because it's long division, okay? It's a little more complicated. So we're going to take x to the third plus 3x squared, and we're simply going to divide that by x squared plus 2x minus 3. So I think I didn't leave enough space, clearly, so let's just throw it up here. It's pretty bizarre. X times x squared is x to the third. X times 2x is positive 2x squared. X times -3 is -3x. We're supposed to subtract, so I'm going to change all the signs. And that gives me x squared plus 3x, which is going to be a 1. X squared plus 2x minus 3. We're supposed to subtract. That gives me, let's see, that gives me x. Was this a positive 3? So was this a negative? This was a negative, and now I made it a positive? Okay, good. X plus 3. So the remainder is plus x plus 3. That's the remainder over the divisor. X squared plus 2x minus 3. Okay, what do we care about the remainder? Not at all. We do not care about it. So it's basically just gone, and this is our slant asymptote. Okay? Because basically our remainder is eventually going to just like go away, because if you actually thought about this one, it's bigger on bottom, 0. So like this is going to go to 0. When you divide by a giant number, you get 0. This is a thing that I want you to understand. Divide by something big, get something small. Divide by something small, get something big. That's it. That's what we have to really kind of grasp, and that will kind of tie into calculus pretty soon. Okay, so let's try a couple. You want to flip the page to page 8 and tell me one that looks not that fun for you, and we can kind of just do it. Now we're going to do the whole thing. 5 has a missing power. 6, 7, they seem pretty easy. Okay, and then we have 8, which is a little more annoying. Okay, so what are you thinking? You want to go for 8? Just go right for it. Rip that Band-Aid off. Okay, sounds great. Let's do it. So as we go down to problem 8, let's kind of scroll down. We'll just do an example. It's going to be very simple, similar to what we've done. I will put up that little yellow sheet here that I kind of have been giving you. So I'll just kind of keep this here and there. So I like to do the domain and range last, but to find the y-intercept and x-intercept, I like to do these first. The y-intercept is when x is 0. The x-intercept is when the top is 0. So I'm going to look at this. I'm going to kind of factor it first. So I can take an x out. That gives me x squared plus 3x minus 4. That gives me x times, hopefully it factors, looks like it will, x plus 4, sorry for drawing so small, x minus 1. That's x plus 4, x minus 1. Is that like ridiculously too small, or you're all right as long as I say it? Okay. I'll make this one better. X plus 2 minus 1. So this is really the function that we want to look at, this function right here, okay? So let me just kind of, this is just bugging me. X plus 4, x minus 1, right? I've got to do a better job because I'm going to keep referring to it. So it was x plus 4, x minus 1. Okay, great. Okay, what we need to do now is kind of important. Let's look at our, let's have our unicorn kind of point to things here, okay? See the unicorn? Do you see a factor that's the same in the top and the bottom? X minus 1? Same in the top and the bottom? What does that mean? There's a hole when x equals 1. So I'm going to say there's a hole at 1 comma something. I do need to figure out what that is, but I'm not going to deal with it at this moment. Do you see a 0 in the bottom that's not repeated in the top? Yes? What is it? X equals negative 2. What does that make that? In the bottom only. Do you know? Vertical asymptote. You don't know? Do you know? You don't know. Okay. Well, I need to know if you don't know. X equals negative 2. If I'm going too fast, I need to explain it better. So we have a vertical asymptote when we set the denominator to 0 and solve. That's it. Set the denominator to 0 and solve. And we can't have it in both the top and the bottom. If it's in the numerator and the denominator, it's a hole. So when we set the bottom to 0 and solve, we have two vertical asymptotes, x equals 1, x equals negative 2, but x equals 1 is repeated, so that's not actually a vertical asymptote, it's actually a hole. Okay. How about x-intercepts, which is when the y is equal to 0. Well, x-intercepts is when the numerator is 0 and you solve it. So I'm going to take the numerator and look at where the numerator is 0. Thoughts on that? Where's the numerator 0? Well, the numerator is 0 here and here. So this is where the numerator is 0. So I have an x-intercept at, let's see, 0, 0, and -4, 0. These are my x-intercepts. I might just plot those. 0, 0, -4, 0. Okay. I might draw in my vertical asymptote. Okay. And maybe it's a good time to plot the hole. Would that be good? Sound like a good idea? Now, this confuses some people. So look at all this information. This is the hole. So you have to find it when there's a factor in the top and the bottom. Find the x. We did that. Now we plug the x into the simplified function. So what we're going to do is we're going to simplify this and then plug in. So let me grab orange, and that will be our hole. Okay. We kind of get rid of that. And now we need to plug 1 in. 1 times 4 times 5 is 5 over 3. 5 over 3 is what we got when we plugged in after canceling. Because if we plugged in before canceling, we get 0 over 0, right? And that wouldn't be helpful. I'm going to go ahead and plot that. It's not beautiful, but it's 1, and it's somewhere between 1 and 2. So here-ish is our hole. Okay? All right. I'm just going to make sure I'm on track, that I haven't made some sort of silly algebra mistake. Looking good so far. Domain and range I like to do later. Y-intercept is when the x's are 0. So when the x's are 0, we have 0 over -2. If we plug in 0 for all of these x's, 0, 0, 0, 0, 0, -2, 0 over -2. So this is also going to be 0, 0, which already was plotted because the x-intercept and the y-intercept are the same, right? In this case, there's only one y-intercept. Otherwise, you don't have a function because it'd be stacked on itself, right? You can only have one y-intercept. Domain and range later. Now it's the horizontal, and what do you think SA means? Slant asymptote, right? Okay. So look at the degree of the numerator. This is the new part. This is what's new for you. Look at the degree of the numerator and the denominator. The numerator is a third. The denominator is a second. Because they're off by 1 power, we are going to divide, long divide, and that answer is our slant asymptote. Now, normally we'd say bigger on top, there's nothing, right? So horizontal asymptote, no horizontal if it's top heavy. It's true, there is no horizontal. But we're still kind of in this same, I don't know. We're still kind of right here. If the numerator is an exponent 1 higher, there's a slant. So this is a little like asterisk, kind of like, don't forget. Just a little like, you know what they call that. What are they? Well, a little exception, I guess. So we're just going to long divide this. And nothing else is really different. Everything else is exactly what you've been taught on the previous lesson or video or whatever you want to call it. So we have x to the third plus x squared minus 2x. We're going to subtract, add. We're going to have 2x squared minus 2x. Okay, pretty good. What are we going to do? I'm not going to take my daughter's card she made me and write on that. That wouldn't be good. I think we'll sneak it in here. Okay. So x squared into 2x squared, that's going to be 2. So we'll have 2x squared plus 2x. Am I still on screen? Hardly. 2x squared plus 2x minus 4. We're assuming that you know this from the last section. That gives us -4x plus 4. That's our remainder. We don't really care about it. So whatever our remainder is, it's gone. So I just kind of put an x there. I don't care. The slant asymptote is y equals x plus 2. That. So I'm going to go up 2 and make a dot, and I'm going to make a dotted line with a slope of 1. That is my slant asymptote. Now, it's kind of hard to see what exactly this thing's doing, but basically you just need to go where your dots are and hug your asymptote. So you need to eventually get close here. You start close, go through your points, and then get close again. That's the general shape. It's not perfect. Is that okay? It's in pencil. Is that okay? Can you see it okay? Because from my angle, I can't see it at all. Thumbs up. All right, thank you. So, and then here we're going to start close, go further away, and then get close again. That's all I need. Okay, it doesn't need to be beautiful. It just needs to go through the hole in the points. That's it. If we look at domain and range, we can now see that everything from negative infinity is good until what number? Well, we can just look here. Our domain is good until -2. Then -2, it's good until 1. And then from 1, it's good until infinity. Range-wise, actually everything's in the range. Pretty weird, because you see how you would think that this hole is going to mess up our range? Well, it's not going to, because there's actually a dot here. So this dot fills that hole, so the range is every number. All the way down, and then there's a hole, but all the way through here. So the range is all real numbers, or negative infinity to infinity. And that is one example on a slant asymptote. So I'm going to see how much time we have. We're probably wanting to cut. They take a little while. Yeah, we'll see you in the next video. Make sure you smash that like button. Tick the notification bell so you don't miss any of the math here. Be sure to check out mrpresario.com for all your mathematical needs. Today is the 16th, so I just want to wish all of my subscribers, all of my Presarians, a happy Pi Day, belated. And we'll see you in the next video. Peace.